Hey everyone, and welcome to this one short video on linear programming problem. This is one of the easiest chapters of grade 12. So let's begin. We're going to talk about LPP, that is linear programming. So now let us talk about linear inequalities first. So what exactly is linear inequalities? So an inequality or an equation is said to be linear if each variable occurs in first degree. So what is the condition? That the variable occurs in first degree and there is no term involving the product of the variables. We'll see some examples based on it. So the first example is ax plus b is less than equal to 0. Then we have ax plus by plus c greater than 0. Then we have ax less than equal to 4. So all these examples are those examples where we have linear inequalities. Basically, if you see, we don't have equal to, right? We don't have equal to. We have less than equal to, we have greater than, or we have again less than equal to here, right? Okay. We can also have greater than equal to, by the way. Linear inequality in one variable. So what is linear inequality in one variable? If you see, we have ax plus b less than 0. This is a example where x is the variable. So how many variables are there? There is only one variable, right? So this is linear inequality in one variable, right? And if I talk about linear inequality in two variables, that means we have x also, we have y also. So there are two variables here, x and y both. So this is linear inequality in two variables. Here also if you see, you have t and s, correct? And y inequality, because if you see, you have greater than and you have less than equal to. I hope this part is clear to all of you. And if you see over here, we have x and y as the variables. Here also s and t are the variables. Now let us see some examples. Solve the equation 5x plus 3y greater than 6 graphically. So we are supposed to solve this equation, linear inequation, graphically. So let us move on to the solution. Firstly, what we will do is, we'll take 5x plus 3y equal to 6. Why? Because drawing the graph of this is very simple. This is a linear equation in two variables, right? And you have already studied in grade 10 that whenever you have a linear equation in two variables, all you need to do is, you need to draw the graph, which is nothing but a straight line, right? Correct. So have a look at this. We'll cut the y-axis where x is equal to 0, right? So put the value of x as 0 basically to get the value of y. So y will be 2. Similarly, if you put y as 0, you will get the value of x, which is 6 by 5. So here it is. These are the 2 points. Basically, if you see this point over here, this point is nothing but your first point 0, 2, and this point is nothing but 6 by 5, 0, and then you just draw a straight line. So this straight line is nothing but 5x plus 3y equal to 6. So 5x plus 3y is equal to 6 is this straight line, but now we have an inequation which says 5x plus 3y greater than 6. So greater than 6 means this will be the direction, right? More than, this is the direction for less than, and this is the direction for more than. So greater than means here, everywhere it will go, correct? So this is how it will look. So this is our feasible region. Anyways, we are going to talk about feasible region later as well, okay? So this is the graph of 5x plus 3y greater than 6. I hope this part is clear to all of you, right? Okay, let's continue. So linear programming problem or linear programming basically, it is an algebraic technique that uses linear equations to find the optimal solution to a mathematical problem. So what is linear programming used for? Linear programming is used for finding the optimal solution to a mathematical problem. Now let us talk about the basic terminologies in linear programming. Now suppose you have ax plus by. Now let's try to understand what is this z is equal to ax plus by. Here firstly we will define an objective function. So what is the meaning of objective function? In life also we define some objective, some goal. For example, if you do a business, you have a goal that this is the profit that you want. You want to minimize the cost. You want to maximize the profit. in your real life also, if you want to lose weight or gain weight, you'll track your calories, right? So that is your objective, that these many calories I need to reduce from my diet, or these many calories I need to increase in my diet. So yes, that is the objective function. So linear function z, which is to be maximized or minimized. So as I told you, maximized or minimized, if you're talking about profit, obviously you need to maximize the profit, right? You want more profit. But if you want to lose the weight, you'll talk about minimizing your diet, minimizing the food, right? So this is the objective function of the linear programming problem. Now that completely depends what linear programming problem we have. Now these x and y, these are called as the decision variables, right? So the linear function z, which is to be maximized or minimized, is called the objective function. So z is called as what? Z is called as the objective function, the objective. And this z is dependent on whom? This z is dependent on the decision variables x and y. Now that can be anything. Decision variables, again, it depends on the question. For example, if you want to have protein and carbohydrate in your diet, so maybe the decision depends on how much protein and how much carbohydrate you need, right? It can be vitamins and minerals also. So the decision variables will be about the vitamins and minerals. X can denote the vitamins, Y can denote the minerals. So it is like that. Okay. Now let us talk about the constraints. So constraints are basically the condition. Constraints means what? Constraint is the condition, right? Or you can say the conditions given are termed as the constraints or restrictions of the linear programming problem. Basically same thing. Constraints are basically what? They are the conditions. Now condition is again the same thing, that my calorie intake should be less than 1800 calories, suppose. So that is a condition, right, on the constraint. My carbohydrate should be less than 500 calories. My protein intake should be less than, say, 600 calories. Sometimes it can be greater than also if I am going for weight gain. So it can be, say, more than 500 calories, more than 600 calories. So maximizing or minimizing, that completely depends on the question or the problem, right? Okay. X and y, both of them are greater than equal to 0. This is always going to be a positive value or equal to 0, always remember. Because here we are talking about some values, right? They can't be negative. Here we are talking about profit, here we are talking about, say, food, we are talking about vitamins, minerals. They cannot be negative, right? So these decision variables, they are always positive, they are never negative. Now let us talk about the non-negative restrictions. So the set of inequalities is known as the set of non-negative restrictions of the LPP. So basically, you are never going to have these negative values here, right? Okay. Now let's talk about the feasible region. What is the meaning of this feasible region, which gives us the optimal solution as well? So the set of all possible values, of decision variables, set of all possible values of decision variables that satisfy the constraints. Set of all possible values of decision variables that satisfy the constraint are called feasible region. Have a look at this. Now we have two lines over here. This is the first line. This is the second line. And it is bounded here, right? It is bounded. So for both the lines, if we have less than equal to here, that is towards the origin, this region is called as the feasible region, which is the common region for both the inequalities basically. This is the common region for what? Both the inequalities. You'll get to know this better once we solve a problem based on this. Now let us talk about feasible region, continue it. The set of all possible values, of decision variables that satisfy the constraint, as we already know. So please make a note of this. This is very important because when you draw the graph, this is going to be very important. Let's talk about inequality. So whenever you have less than equal to, your feasible region lies on the origin side. Feasible region lies where? On the origin side. Whenever you have greater than equal to, the feasible region lies on the non-origin side. So feasible region lies on the origin side when you have less than equal to, feasible region lies on the non-origin side when you have greater than equal to, and the feasible region lies on the line when you have equal to. Clear? Okay. Have a look at this. So when you have less than equal to, I am talking about this part. When you have less than equal to, the feasible region lies towards the origin. That is, see the direction, this direction, right? Towards the origin. So you can have this bounded region as the feasible region. That is the triangle region here. Similarly, non-origin side. So this is the feasible region. It is not going to have any boundation there. It will not bound. It will go on and on because there is no blockage here, right? And then on the line. So if you have equality, we already know whenever we have equal to, the line itself will be the feasible region. The line itself is going to be the feasible region, right? Okay, let's continue. Let us talk about the optimal solution. What is an optimal solution? Optimal solution is a feasible solution that results in the maximum or minimum value of an objective function. So optimal solution is what? It is the feasible solution that results in the maximum or minimum value of an objective function, right? So here it is. Now have a look at this. We have some objective function and then we have all the constraints and the inequalities, and see all the lines over here, the pink lines. This is the bounded region, right? So this is the optimal solution here. This is the optimal solution, which is bounded by all the lines. Again, because we don't have an example right now, it's very difficult to understand what exactly is going here. But don't worry, just understand what is feasible region. You will get to know this better once we solve actual problems based on this. Now, how do we formulate an LPP or LPP? So, step 1 is we identify the decision variables. We identify x and y. Depends, you can have more variables also. Then step 2 is we write down the objective function. Firstly, we will identify the decision variables. Then we will write down the objective function. Then step 3 is we will formulate constraints. We are going to formulate constraints. Let us see an example. So a factory manufactures two products A and B. Factory manufactures two products A and B. So to manufacture 1 unit of A, 1.5 machine hours and 2.5 labor hours are required. And to manufacture product B, 2.5 machine hours and 1.5 labor hours are required. So in a month, 300 machine hours and 240 labor hours are available. Profit per unit for A, so for A means this, that is 1.5 machine hours and 2.5 labor hours which are required. The profit for A is rupees 50 and the profit for B is rupees 40. We are just supposed to formulate the LPP here, right? Let us see the solution now. So step 1 is what? We will identify the unknowns. So here we are talking about the two unknowns, right? So let X be the number of units of A manufactured per month. So here we are talking about the number of units of A manufactured per month. Then we have B also. So we can take that as Y, some other variable. So Y be the number of units of B, right? The product B you can say, manufactured per month. So we have identified our decision variables X and Y, which is number of units of A and number of units of B, right? And then obviously X and Y, we are talking about some products here, they cannot be negative. So non-negative constraints X and Y are greater than or equal to 0, right? What is step 2? We will formulate the objective function now. That is, we need Z, right? We will formulate the objective function in terms of what? In terms of X and Y. So here what are we supposed to do? Obviously here we are talking about a manufacturer who is making some products, he is trying to make money out of it. So can I say profit per unit, right? So here we are talking about profit. So Z be the profit function. So can I say we need to maximize the profit, right? Who will try to minimize the profit? Obviously, we will try to maximize the profit. Even if it is not given in the question, it's a common sense, right? You want more profit. So to maximize the profit, we have 50x plus 40y. 50x plus 40y, right? So to formulate constraints for machine hours, just focus on the machine. 1.5 machine, 2.5 machine, and in a month, 300 machine hours are required. 300 are available. So maximum 300 are available, maximum. So can I say 1.5x plus 2.5y is less than equal to 300? Now if I talk about labor hours, for labor it is 2.5 and 1.5 and 240 are maximum available. So 2.5 plus 1.5 is less than equal to 240. Obviously x and y. For machine A, for machine B. See, this is for machine A, it's better you can say product A, okay, and this is for product B. X and Y, both of them are greater than equal to 0. So, the required LPP is, firstly, we have described the objective function Z, which is the profit function. We are supposed to maximize the profit. How are we going to maximize the profit? 50x plus 40y, we need the decision variables x and y for that. And then such that the condition is 1.5x plus 2.5y is less than equal to 300 for product A and B. We are talking about the machine hours, and obviously we need to reduce the time so that you will increase the profit, right? Because the moment you reduce the time over here, then only you can maximize the profit. The labor hours, the machine hours, need to do it quickly. That's why less than equal to, correct? And then finally you write down x comma y is greater than equal to 0. So I hope you have understood how to formulate LPP. It's very simple. As of now we have just seen how to formulate LPP. Going forward we are also going to see how to draw the graph, also find out the feasible region, also find out the optimal solution, right? Okay, anyways, let's continue. Now comes the actual part, that is the graphical method of solving linear programming problem. So what is the graphical method and what are the steps involved? Firstly, what we need to do is we'll formulate the problem. That is, we'll define the objective function and the constraints. We're going to define the objective function, we're going to define the constraints. Then, whatever inequalities you get, we will convert those inequalities to equations. We'll convert what? Inequalities to equations. Then, we'll rewrite each inequality constraint as linear equation. Then we will rewrite it as linear equation. So let us talk about the graph of the equation. So we'll plot each equation on the Cartesian plane, and remember, whenever we plot the equation on the Cartesian plane, here we are talking about drawing a straight line because we are talking about linear equation, right? And then after that we'll identify the feasible region. That is, we'll determine the region that satisfies all constraints. That is the area where inequalities overlap. Now let us talk about the corner points. How do we determine the corner points? So locate the vertices of the feasible region, as the optimal solution is often at one of these points. What we will do is, we'll locate the vertices, that is, we'll locate the points basically. Something like this. Then whenever you get the optimal solution, whenever you get the feasible region, you locate these points like this. Suppose this is your feasible region. And then after taking the feasible region and the vertices of that, one of these points will give you the optimal solution, which is to maximize or minimize, right? Then we will evaluate the objective function. That is, whatever coordinates you get, you'll get some coordinates of x comma y, right? So whatever coordinates you get, we'll substitute each corner point in the objective function y to maximize or minimize the value, depending on the question. Either you will maximize or minimize. So let us see an example now. It says, solve the following linear programming problem graphically. Solve the following linear programming problem graphically. Maximize z is equal to 4x plus y. So we are supposed to maximize z is equal to 4x plus y. So this is our objective function, right? So what are the constraints? Constraints are given: x plus y is less than equal to 50, 3x plus y is less than equal to 90, x is greater than equal to 0, y is greater than equal to 0. So obviously this is anyways going to be there. Okay. Now what we will do is we'll convert these inequalities into equations. Firstly, we have x plus y less than equal to 50. Can I write this as x plus y is equal to 50? Correct? From inequality, we went to equality. So here, let us draw the graph of x plus y equal to 50. For that, obviously, we need what? We need the values of x and y, right? And we need the values of the coordinates. So if I put y as 0, I get x as 50. When I put x as 0, I get y as 50. Basically, when I put y as 0, I get x as 50. When I put x as 0, y as 50. So what are the coordinates? The coordinates are 50, 0 and 0, 50. I hope you are understanding the coordinates here. 50, 0 and 0, 50. But here we have less than equal to 50. We have less than equal to 50. So where will the feasible region lie? The feasible region will lie towards the origin, right? Feasible region will lie towards the origin. Then we'll take the second equation, which is 3x plus y less than equal to 90, right? So can I say this is 3x plus y equal to 90? Again, you draw the table of values. Here, you put y as 0, you get 3x as 90, x as 30. You put x as 0, you get y as 90. So this becomes 30, 0. This becomes 0, 90. And what is the feasible region? The feasible region again lies towards the origin because we have less than equal to 90. Since we have less than equal to 90, feasible region is going to lie towards the origin, right? Now we'll plot the constraints, that is x plus y equal to 50 and 3x plus y is equal to 90 on the graph. We're going to plot this. Here it is. Now we have two lines. This is the first line, the brown line, which is x plus y equal to 50. Then 3x plus y is equal to 90. This is the blue line. 3x plus y is equal to 90. So, if you see this, the blue line and the brown line, here what do we have? We have the feasible region. After getting the feasible region, you will have the corner points, right? See here. So these are the corner points. We'll focus on the corner points as well. So the feasible region will be the bounded region by points OA, BC. OA, BC, right? So these are the corner points, right? O, A, B and C. These are the corner points. So since these are the corner points, for O, origin, we have 0, 0. For A, where is A? A is 30, 0. For B, we have 20, 30 and for C, we have 0, 50. So all these are important for us. These are the corner points, right? So once you get these corner points, what we are going to do is, we are going to substitute all four of them in our objective function to check and maximize it. Let us see that. So z is equal to 4x plus y. Where is this coming from? This is coming from the question only. If you see, we are supposed to maximize, right? Z is equal to 4x plus y. But now we have the values of x and y, isn't it? Now we have all the four values of x and y here. So let us first put 0, 0. Then we will put point A 30, 0. Then we will put 20, 30. And finally we are going to put 0, 50 and check which value is the maximum value. So here if I put 0, 0, obviously this is going to be 0. 4 into 0 plus 0. Let me put 30, 0. That is 4 into 30 plus 0. 4 into 30 is 120. 120 plus 0 is 120. Then let me put 20, 30. That is 4 into 20 plus 30. 80 plus 30 is 110. And then finally let me put 0, 50. That is 4 into 0 plus 50. Observe the values. 0, 120, 110, 50. Which value is greater? Can I say 120 is the biggest value here? That means this is our optimal solution. So here we can say that the maximum value z, which is equal to 120, it is occurring at the point A, 30, 0. So clearly we can say that the optimal solution, right, best solution, the optimal solution to this particular linear programming problem is obtained at which point? It is obtained at the point A, whose coordinates are 30, 0. Clear? And at this point, the maximum value is how much? At this point, the maximum value is 120. Now let us talk about the main types of linear programming problem. They include manufacturing problems, then they include diet problems, they include transportation problems. We are going to talk about manufacturing problems, diet problems, transportation problems. Let us talk about manufacturing problems. So manufacturing problems, they involve determining the optimal production levels of products to maximize profit or to minimize cost. So whenever we are talking about manufacturing problems, the agenda or the goal, or you can say the objective, is nothing but to either maximize profit, you want more money, or you want to reduce the cost. Either of these two. Let us see an example. So a factory produces two types of products, each requiring a certain number of labor hours and raw materials. So there are two things. It requires labor hours, that is you have to pay the laborers on the hourly basis, and you also require some raw materials, right? You need to purchase some goods. Given the availability of these resources, the goal is to find the quantities of each product to maximize the profit. So what is the objective? The objective is clear. The objective is to maximize the profit, right? Let us see an example. So a company produces two types of TVs. So two types of TVs are produced by a company. One is black and white and the other is color. So one TV is black and white TV and other is color TV. The company has the resources to make at most 200 sets a week. Now this is very important. Whenever you are reading, read this carefully. At most. What is the meaning of at most? At most means maximum. So the company has maximum, how much? The resources that can make maximum 200 TVs. So can the company make more than 200 TVs? Never, because that's the maximum capacity. So can I say they can either make 200 or less than 200. So this is going to be less than equal to. Now creating a black and white TV, it is costing rupees 2700 and 3600 rupees is the cost to create a colored set. The business should spend no more than 6,48,000 rupees a week. So their maximum budget, again see, maximum money that they can spend is 6,48,000. So they cannot go beyond that. It benefits from rupees 525 per set of black and white and rupees 675 per set of colors. So from black and white TV, it is benefiting 525 rupees. And from colored set, it is benefiting 675 rupees. So how many sets of black and white and colored set should it produce in order to get the maximum profit? So the question says, to get the maximum profit, how many sets of black and white and colored set should it produce? We are supposed to formulate this using LPP. Let us talk about the solution now. Now, do we know how many black and white TVs are produced? No. So what we will do is, we will consider that as X. So let X be the number of black and white TVs produced per week. And then the second type of TV is color TV. So let Y be the number of color TV produced per week. Now let us talk about the objective function. What is the objective? The company wants to maximize the profit. The company is wanting to maximize the profit. So the objective function, how can you define it? The objective function can be defined as Z is equal to 525x plus 675y, right? We are supposed to maximize this. Now company can produce what? At most, that means maximum 200 TVs, sets of TVs per week. So can I say black and white TVs plus color TVs maximum 200, so less than equal to 200? Yes. And what is the maximum budget? The maximum budget is 6,48,000. So can I say here 2700x, because for one TV of black and white 2700 rupees is needed. For one color TV 3600 is needed. So 2700x plus 3600y, the maximum budget is 6,48,000. So this will be less than equal to 6,48,000. If I divide this further, we are dividing by what? 900. If I divide by 900 on both the sides, I get an equation 3x plus 4y less than equal to 720. Okay, let's continue. And the constraints obviously are non-negative. X and Y are what? They are black and white TV and color TV. Now, number of color TV and black and white TV cannot be negative anyways, right? So these are non-negative constraints. So firstly, let us see what is the required LPP. We are supposed to maximize the profit. So it is a profit function. Maximize Z is equal to 525x plus 675y, because 525 is the profit per black and white, 675 rupees is the profit per color TV. X plus y is less than equal to 200 and 3x plus 4y is less than equal to 720. So recall our previous example. What we do? Firstly, what we do is we'll change this inequality to equations. So can I say this becomes x plus y is equal to 200 and 3x plus 4y equal to 720. Okay, we have done this directly. You know how to do this. Put y as 0, x is 200. Put x as 0, y is 200. So 200 comma 0, see here, 0 comma 200, just join it. Same thing you can apply here. You can put x as 0, you get y, you put y as 0, you get x. Now once you get this, and because it is less than, it is moving towards the origin, right? But what is the common region here? The common region is this part, the blue region, that is called as the feasible region, right? The blue region is called as the feasible region. Now once you get the feasible region, you see the corner points, 1, 2, 3, 4. So these are the corner points, right? Now once you get the corner points, take the coordinates and then put it in the objective function, right? Now once you put it in the objective function, you will get the maximum value. Whatever the maximum value is, that will be your profit. Let us do that. Okay. So this is our objective function. So first, the coordinate is A, 200 comma 0. The value is 1,05,000. For B, the value is 1,21,500. That is 0 comma 180. For 80 comma 120, the value is 1,23,000. And at 0 comma 0, obviously there will be no profit, right? Because you are not producing anything, how will you get the profit? Anyways, so in this 3, which is the maximum value? Can I say the maximum value is this? 1,23,000. So since 1,23,000 is the maximum value, we can say that the manufacturer has to produce 80 black and white TVs and 120 colored TVs. So if he produces 80 black and white TV and 120 colored TV, he is going to get maximum profit. So see how LPP is so important in real life also. This is related purely to business, right? Okay. So yes, company should produce 80 black and white and 120 colored TV set to maximize the profit. So we have seen an example of manufacturing. We'll also see a problem now which is related to diet. So the diet problems basically aim to determine the optimal combination of food items to meet nutritional requirements at the lowest possible cost. Obviously, we want good nutrients to get into our body with less cost. This is obvious, right? So what is the objective? The objective is to minimize the cost while satisfying the dietary requirements. Let us see an example. So a person needs to plan their diet to meet daily nutritional needs like the protein, vitamins, carbohydrates, minerals at minimal cost. How? By combining different food options. each with specific nutrient content and price, right? Let us see an example. So there is a health enthusiast. He or she wishes to mix two types of foods in his diet. Okay, he's a person, he's a guy, in such a way that the vitamin content of the mixture contains at least 10 units of vitamin B and 13 units of vitamin C. At least, that means minimum 10 units of vitamin B is needed and minimum 13 units of vitamin C is needed. So we need greater than this. We need more than this, right? Now, since there are two types of food, so we have F1 and F2, right? So food F1 contains 1 unit per kg of vitamin B and 2 units per kg of vitamin C, and the cost of that is 60 rupees per kg. There is second type of food which contains 2 units per kg of vitamin B and 1 unit per kg of vitamin C, and the cost for this is 80 kg. So this is the question first of all. Students, you have to read the question very carefully because everything is there in the question only. All you need to do is formulate the LPP correctly. Once you formulate the LPP correctly and then you put it on the graph, find out the feasible region, find out the corner points, get them, put it in the solution, you get the final answer, right? Okay. So here let us talk about the solution now. So what is the objective? We are supposed to frame a diet plan by creating LPP model to minimize the cost of the mixture, right? We are supposed to minimize the cost of the mixture. So there are two types of food, right? So let X be the amount of food F1 and Y be the amount of food F2. So the objective function to minimize the cost will be minimize Z is equal to 60X plus 80Y. Why 60X plus 80Y? And why minimize? Because 60 rupees is needed for food 1 and 80 rupees is needed for 1 unit of food 2. So we are supposed to minimize that. Okay. But if you see the constraints here, we need vitamins and mineral minimum, right? So here we can say that vitamin B requirement is X plus 2Y greater than equal to 10. Where are we getting this from? Right, here we are talking about vitamin B, 10 units of vitamin B, at least, right? At least 10 units of vitamin B. So we are talking about vitamin B, and food F1 contains 1 unit of vitamin B. See, so this becomes 1 into X, which is X, and 2 units of vitamin B for food 2, which is 2Y. So this is X and this is 2Y. X plus 2Y greater than equal to 10. Similarly, for vitamin C, we'll have 2X plus Y greater than equal to 13. Again, if you see Y, for vitamin C, see, you have 13 here, 2 units of vitamin C, 1 unit of vitamin C. So 2X plus Y greater than equal to 13. And then the non-negative constraints, that is X is greater than equal to 0, Y is greater than equal to 0, right? Okay, now once we have this, all we need to do is we need a graph. So the required linear programming problem is okay. The same thing again. So yes, this is correct, this is correct. And then we can plot the graph. Let's understand the graph. X plus 2Y greater than equal to 10. Now if you see this is greater than X plus 2Y greater than 10, and this is 2X plus Y greater than 13, right? So the feasible region is here. Now there is no boundation. So what are the corner points? Corner points, this is a corner point, this is a corner point, this is a corner point, right? So we'll substitute that here. So if I substitute 0, 10 here, I get 800. If I substitute 9, 2, I get 700. And if I substitute 13, 0, I get 780. Our objective was to minimize the cost. Minimize, right? Minimize the cost here. So which is the less cost? Can I say the less cost is rupees 700 and we are getting it at 9,2. So the minimum cost is rupees 700 at C 9,2. So here we can conclude that to minimize the cost, the diet plan should consist of 9 kgs of food F1 and 2 kgs of food F2. So we need 9 kgs of food F1 and 2 kgs of food F2 to minimize the cost. I hope you are understanding how important LPP is in real life to also solve problems based on diets, transportation, manufacturing, profits, losses, businesses, right? So I hope you enjoyed the session with me on LPP. This is one of the simplest chapter of grade 12. You don't have to do anything much in this, purely based on logic. Thank you so much and learn with top scholars.